Hello Chem 1B, this is chapter 16, lecture video 6, and in this lecture video we're going to be talking about mixtures of acids. And really there are kind of three different scenarios that you might be faced with in questions on tests or quizzes, or our check-in problems, for instance. And that is really, hey, we have a mixture where two acids are being mixed together or are already mixed together and they're both strong acids. Another example is one of the acids is strong, being mixed with something that's a weak acid. And the third example that I don't have on this slide, but we'll see later in this lecture video, is where we have a mixture where both acids are weak. So when both acids are strong, we pretty much can assume that whatever their concentration is in the solution is equal to the H3O plus concentration for each individual strong acid, and then we can just add them together for the most part. And we'll do a problem like that on the next slide. If one of the acids is strong and the other acid is weak, it really depends on what the question is asking. We can still assume that the strong acid dissociates 100%, so that's pretty much going to be equal to the H3O plus concentration. And if you're being asked for the pH, really you can completely ignore the weak acid and just go, oh, whatever the concentration of the strong acid is, that's the H3O plus concentration. Take the negative log. There's your pH. However, if you're being asked for, hey, what's the concentration of everything present in the solution, then you're going to need to do a nice table problem. And we'll talk about that in a problem after the next slide. So basically the reason why this is the case is because we have so much H3O plus present initially, it kind of causes Le Chatelier's principle to really barely move the equilibrium to the products, even though we have a zero here. There's a very little shift this way because of the H3O plus concentration already being there initially from the strong acid. This decreases the amount of ionization of the weak acid even further than usual, which means it pretty much doesn't make a difference to the pH. So if we're just trying to calculate pH, the weak acid's concentration is really not going to affect our H3O plus concentration to any great extent unless we have a really large Ka, or our strong acid concentration is super duper low. Those are kind of rare cases though. However, if we're asked to solve for the concentration of everything present, like for instance the conjugate base, well that's this guy, then we're going to need to do an ice table. So we'll do a problem like that a little bit later. So let's do two problems involving strong acids. And really there's two kind of forms this could take. One where we already have the concentrations of our strong acids present in the solution. So in this first problem, you can see that we're told that the solution contains this amount of HCl and this amount of HNO3. Both are strong acids. Well, that means from the HCl, the solution contains 0.0054 molar H3O plus, and from the HNO3, the solution contains 0.0013 molar H3O plus. Now, then the total H3O plus is just really the sum of these two, because they're already in the same solution. We don't need to worry about volumes here in this problem, which tells me that the sum of these two is going to be equal to 0.0067 molar. Now to get pH, I can just say, hey, negative log of 0.0067 gives me my pH of the solution. And that's the whole problem here in this case, which gives me a pH of, pretty acidic. Obviously, our pH in this case should be around 2.717, sorry. Now, this problem here is a bit different because we don't know what the concentrations are of our strong acids in the solution. We know what they are before we mix them together, right? I know that I have 25 mils of this concentration of HBr and 15 mils of this concentration of HClO4, or perchloric acid. I don't know what their concentrations are in the final solution. And so I can't just add their two concentrations and say, hey, the molarity of H3O plus is 0.03. It's not. So we need to calculate moles to do this. So I'm going to take my 0.025 liters. I basically just converted milliliters to liters here. And I'm going to multiply that by my 0.015 molar HBr. And that's going to get me my moles of HBr. I'm going to do the same thing with the perchloric acid, multiply my volume of it in liters by my concentration of it. This will give me my moles of HClO4. Now these guys are effectively going to be equal to moles of H3O plus. So if I calculate those values, I get 0.000375 here and 0.000225 there. Now, if I want the total moles of H3O plus, because these guys are equal, we really just need to add these two values together to get our total moles of H3O plus in solution, right? Which is going to be equal to 0.000600 moles. Now I can't use moles in my pH equation because it's the concentration of H3O plus that I need. So I need to divide this by the total volume now in liters. So in other words, my concentration of H3O plus is equal to 0.000600 moles over 0.0. I got to add my 25 to 15 milliliters together. That gives me 40 milliliters or 0.040 liters. And so I can get that concentration now. And I get my concentration is 0.015 molar. This means I can now take the negative log to get my pH, which is equal to 0.015 molar. Negative log of that is going to give me my pH of the solution, which is about 1.82. And so these are the kind of two types of problems you might see for a mixture of two strong acids. All right, so let's do a problem that has a strong acid and a weak acid involved, right? So we have HBr, that's our strong acid, and we have formic acid, that's our weak acid, right? Now, I know that the HBr with water is a one-way dissociation, right? So all of our H3O plus is going to be formed from HBr, and all of our HBr breaks up to form it. So basically what this tells me is that because I had 0.10 molar of this initially, I'm going to get that much of both H3O plus and Br minus. And at the end of the day, I won't have any HBr left because it dissociates 100% into these two things. But formic acid is a weak acid. It goes to equilibrium. Now, I don't know what I do know what the formula of formic acid is, but we're just going to use HA. So I know that it is 0.50 molar formic acid initially because that's what it tells me in the problem. I know I don't really care about water. I know that A minus's initial concentration is 0. And this is where things get tricky. H3O plus is not 0. We have H3O plus initially in the solution from our HBr. So its initial concentration is 0.1 molar. Now at this point we can fill in our ice table as per usual. We do minus x plus x plus x. We get x, 0.10 plus x, 0.50 minus x. And we can set this all up and set it equal to our Ka value, right? So 0.10 plus x times just x all over 0.50 minus x. This has to be equal to our Ka, or 1.8 times 10 to the negative 4. I'm going to use the 5% rule here because I know I'm allowed to, but you should always double check after you do it. So we're going to cross off both the plus and minus x because we're going to assume x is really small and doesn't really change those two concentrations we're adding and subtracting it to. At this point, we can solve for x, right? So let's do that on the next slide. So this is basically what we canceled our equation there too. And I'm just going to multiply both sides by 0.5 and divide both sides by 0.1, and I get that x is equal to 9 times 10 to the minus 4. If you double check your 5% rule, we're totally good. That's way less than our initial, which is 0.5. We can plug that into the equilibrium row. 0.5 minus x is, to all intents and purposes, still just 0.5, especially if we're rounding to 2 sig figs. H3O plus 0.1 plus 9 times 10 to the negative 4 is still pretty much 0.1. Really, this is the only reason why we had to do that ice table, was to figure out what x was, because that's what our formate concentration is, or our conjugate base concentration is. We can also calculate the OH minus concentration if you wanted to, right? We know Kw is equal to H3O plus times OH minus. So if I know H3O plus is this guy, I can plug that in here. Kw is 1 times 10 to the negative 14. Solve for OH minus, you get 1 times 10 to the negative 13. We could solve for pH if we wanted to using this guy. It's 1. You should always check that your 5% rule is there. Let's do one more example here of a mixture where both acids are weak. In this type of scenario, we have a little bit more work to do. Generally, if the Ks are simpler, we must do what we call a double equilibrium problem, which is not something we're going to see in this class for weak acid mixtures, but it might be something in a more advanced chemistry course if you're a chemistry major. So most of you probably won't ever have to see that. In our case, we're always going to have Kas be substantially different from each other when we have mixtures of 2 weak acids. So meaning one of them is going to be way larger than the other Ka value, generally by a factor of about 1,000. In this scenario, we can kind of solve for the pH of just the stronger of the 2 weak acids, meaning the one with its Ka being larger. We're going to pick that one. If we're just trying to find pH, then we just solve for the H3O plus concentration using that first weak acid, the one that's stronger, and then completely ignore the second weak acid. Generally, that works totally fine. However, if we're being asked, like in the last problem, to solve for the concentration of everything present in the solution, well, then you're going to need to do 2 sequential ice tables. So we're going to do the stronger Ka first, then we'll plug the values we get from that into the weaker Ka's ice table and solve that. And we're going to do a problem like that in just a second. So let's do that. Okay, so in this problem, we have what is the concentration of everything present in a solution that is 0.5 molar formic acid, here's that Ka, and 0.2 molar hypochlorous acid, here's that Ka. Now, if we notice, formic acid is definitely a larger Ka, so formic acid is the stronger of the two. Hypochlorous acid is very weak in comparison. We're going to do formic acid's equilibrium first because it's the stronger acid of the two. So let's write out its equilibrium. There that is. We're going to fill in this ice table. We know that it is initially 0.50 molar. We know we do not care about water. Initially, we have 0 H3O plus and 0 formate. And we can just, fill in our change row. And we get our equilibrium row. And we can solve this according to the Ka equilibrium, right? So we have Ka is equal to 1.8 times 10 to the negative 4, and we know this is products over reactants, so x squared over 0.50 minus x. Now, I'm going to use the 5% rule here because I know I can, but in most cases we can for weak acids. I would generally do it, but then always double check if it was okay. It will be okay in this scenario. This means that x is really just going to be equal to 1.8 times 10 to the negative 4 times 0.5, and then you just take that to the power of 1/2 or square root it, and you're going to get 0.00949 molar for x. Now at this point, if we had been asked for the pH of the solution, we're pretty much done. You just take the negative log of x because that's our H3O plus concentration, and then you'd be done. You completely ignore the hypochlorous acid. That's not what we were asked in this case, so we need to do a little bit more work. So again, we solve, we get that effectively if you round. That for x if you round. Again, to get this one, we just multiplied both sides by 0.5. Our assumption that x is small is valid. It is, in fact, less than 5% of 0.5 molar. We can now plug into our equilibrium row and get the rest of the values, right? So if we plug these and subtract, we get 0.49. Our H3O plus concentration is 0.0095. Formate concentration is 0.0095. And we can move on to the next ice table now. Because we want the concentration of everything present in the solution, we need to figure out what the concentration of hypochlorous acid is after the equilibrium is established, and hypochlorite, what its concentration is. So we now solve this as though it was that original one that we did a little while ago, the strong weak mixture. We know that our initial concentration of HClO was 0.2 molar from the problem we were given. Again, we don't care about water, still a pure liquid. Our initial concentration of H3O plus is what we determined from the previous ice table, right? So that's going to be this guy here. And we have 0 initially of hypochlorite. So now we just fill in our change row, minus x plus x plus x. We get x, we get 0.0095 plus x. We get 0.20 minus x. And we can set this equal to the Ka value, which I believe is 2.9 times 10 to the negative 8. And set that equal to products over reactants, right? So 0.0095 plus x, all that, times x over 0.20 minus x in the denominator. Now again, I'm going to use the 5% rule. This is a super small Ka value. 5% rule is definitely going to be okay here. You can pretty much not even bother checking, but always check just to be sure, honestly, but it's going to be fine. So effectively, this means that my equilibrium expression is 2.9 times 10 to the negative 8 is equal to 0.0095 x all over 0.20. And this is a pretty simple equation to solve for, right? We can just multiply both sides by 0.2 and divide both sides by 0.0095. You're going to get that x is equal to about 6.1 times 10 to the negative 7, which is super small. So at this point, we can kind of plug into our equilibrium row here. 0.2 minus 6.1 times 10 to the negative 7 is pretty much still just 0.2. And then H3O plus that, still pretty much 0.0095, especially if you consider sig figs. ClO minus, on the other hand, is equal to x, so that's the whole reason for doing this. If you wanted to, you could again calculate OH minus in the equation from Kw, and you get a slightly larger concentration than the last example, but still, it's pretty small. All right, so if you have any questions, just let me know. Discussion session or email is the best way to get a hold of me if you have any questions. Again, sorry, the assumption was totally valid. This is definitely less than 5% of the initial concentration of 0.2. All right, so that's it for this video.